This is IPv6. This is the whole reason I did the whole number conversion thing, so you have a clue what I'm talking about here. Okay? IPv6. This is made by Ken Dewey and others, which means I did a whole pile of research, days worth. Because did anyone ever look at the book, how much they say about IPv6? There's not much. And there's not much out there. So I tried to come up with something that was halfway usable. So let's walk through this. Okay, you're not going to be totally responsible for everything as much as in my other class, but it's still nice to know. Okay? IPv4 says uses address that are 32 bits in length. We have 4 numbers, 8 bits each. That's 8 times 4 is 32. 4, what's that? That's 4 billion possible addresses. Only a fraction of those can actually be used. There's a lot we can't use. But say we could. Say we could use all of them. 6.5 billion people on the planet. They all want internet access. Okay, each of you can have 0.66. And that's not even enough one for every person. So it kind of sucks. Y'all agree with that? Then what if we want to start having our laptops and our cell phones and everything else with an IP address? Now, if you have if you have a cell phone, you got an IP. If you got a wireless router at home, you got an IP. If you got a cell phone, you got there's some of us have many addresses. Okay, that's not enough. Before long, everything's going to have an IP address. Everything. I did a presentation on 4G LTE the other day, and it's at the point where everything will be able to communicate via that, and it's going to be fast enough to handle it. So we're going to, what they're saying in 2014, I think they're saying, pretty much 3G will be gone. I mean, it'll be there, but no one will use it. It's kind of like, it's... Yeah, it's, 2G I actually use quite a bit. Edge, I still use because it's better on the battery. My battery lasts 3 days easy. The point is, we don't have enough addresses. IPv6 uses a 128-bit address scheme. Okay? 64 bits for the network, 64 bits for the host. That's that many IP addresses. So instead of 4 billion, we have that many. Is that enough?
Is that even a real number?
That's the exact number. Each person on Earth, all 6.5 billion of us, could each have 50 octillion addresses. So every person on Earth could have this many addresses. Dude, I could put one on every blade of grass in my yard. Just think we could have an IP-enabled lawnmower. I could tell exactly which blade to go mow. But, I mean, is that enough addresses or what? That is a lot of stinking addresses.
I think that's overdoing it.
Yeah.
No!
But, a lot of places say 50 octillion, but I think when you see that many zeros, you're like, isn't that just amazing? Okay, so it's made up of 8 groups of 4 hexadecimal digits. That's hence the hexadecimal thing I showed you a minute ago. So here's an IP address. We have 8 groups. 1, 2, 3, 4, 5, 6, 7, and 8. 8 groups of 4 hexadecimal digits. So if that's true, then what the heck happened here? And what happened here? Why is there only 1 0? Because remember, 1 0, 2 0, 3 0, 4 zeros, there's still a 0. Hence the first slide on the other lecture. But this guy here, since I told you it's made up of 8 groups of 4, then what the hell just happened?
Just put zeros in front of the rest of them for the other 6 groups.
Actually, this is exactly how it gets written. I'll show you why. Okay, the rules are, for shortening it, it says any leading zeros are dropped. So, 0600 becomes 600. Okay? So 002 becomes 2. 03 becomes 3. Easy enough. 2 or more groups of zeros can be replaced by 2 colons. You can only do it one time. So 4 groups of zeros can become 2 colons. Okay? So this address here, how many groups of zeros are there? Well, since we know there's a total of 6 areas, 8. There's 8 areas, but we only see 2, so obviously we're missing 6. There's got to be 6 here. That's the way you figure out how many zeros there are. We know it's a group of, there's 8 groups of 4 hexadecimal digits. So when we say, okay, I'm showing you 2 groups, so we're missing 6. So obviously, if we wanted to write it out, we had to include 6 zeros. So that works? Okay. Easy enough?
That's really easy.
It is.
Gets easy.
Yeah, you know, but we're gonna go on.
How are you to know?
Go ahead.
It shows you're missing 6, so you just assume there's 6 there.
I know there's 6 there.
Okay, but how do you not know that there's 5 there and a 0 in the front? Then
It can't be.
5?
You can't be, because the only way you can replace is when you have 2 or more groups of zeros together, and you can only replace one time. So I could have a 0 in the front, but I would have to show it.
Okay.
But it would be 0 colon. I couldn't just have a 0. It would have to be 0 colon FF06. I couldn't just.
And
So I'm
then
saying.
Since that 0 is there, then you can assume that the other 5 that you need is within the 2.
Exactly.
total.
Yes. Okay. Good question. All right. Header compression. Look at our differences between our IPv4 and our IPv6. Top is IPv4, bottom is IPv6. So we're getting more complex, yet it looks a lot darn simpler, doesn't it? So getting rid of a bunch of junk. Our headers are fixed length now, so get rid of that. Get rid of type of service crap. Get rid of that stupid flag things no one liked anyway. Get rid of header checksum. What's a checksum again?
Verifies that everything's
Right. It's verify that it's not screwed up. So we're getting rid of that. What do you think?
Why?
That's a very good question. That's why I made everything that would make questions in red. Well, the header contains TTL, which changes with every hop. Remember we talked about TTL last time, the time to live? Every time we go through a route or decimins, that's how traceroute uses. So what was happening to happen was, every time we went through a router, our header, we would have to recalculate the checksum, update the checksum. So you can see how that would get quite old. So we're doing a lot of extra work. Okay, so it requires it to be done at every time. This is already done in the IP layer anyway. The IP layer where the data is, we automatically do it, so why do it here again? That's why. Because we're already doing it somewhere else. So why should we worry about doing it in the header when the data we're already doing it? Okay, speeds up routing, processing. And I understand why they want that there, but do you really need it there?
So we're supposed to be switching to IPv6 by 2014.
We're switching now. We're already switched. A lot of places have. A lot of places have already implemented it. The deal is it is backwards compatible. 100%. So that was one of the goals of it. Hey, if we want to use IPv6, we need to make sure it works with IPv4. So what's going to happen is our backbones, our connection to Cox is going to become an IPv6 address. So our cable modem is now going to have an IPv6 address. But internal to our house, we can still use IPv4 all day long. No problem at all.
So they start giving my 50 octillion
Yes.
IP address.
What's going to happen is, you know, those places that charge you for 5 IP addresses, dude, you're going to have, it's not quite 50 octillion, but it's very darn close for every person. So it's,
Yeah, Cox is already issuing out the IPv6.
is there? And you can get your IPv6 address now. I can't remember. I didn't write the address on there either. It's like, begins with H. It's something electric, like Horizon Electric or something like that. Get a free IPv6 address for life. So, Hurricane Electrics, that's the company. HurricaneElectric.com. You can go there and you get your address. Okay, I don't know why it's Hurricane Electric. That's just what it is. Okay. All right. So addressing. This interface can have multiple addresses. Just like in IPv4, we can actually have multiple addresses on an interface. I didn't show you guys that, but we can. A prime example is like a web server. When I ran my hosting business, I had many, many addresses all on the same machine. Can you imagine if every website had to have a separate machine? I hosted 300, 400, 500 websites. I would have 300, 400, 500 servers. That would suck. And you know, and if you think about it, a lot like GoDaddy charges $8. It's like $8 a year for hosting. No, it's $8 a month or $80 a year. That's what it is. So for $80 a year, I can host a website. So obviously, that's not going to buy a server. So what we can do is we can multiple addresses on the same machine. You can do the same thing here. Okay. The addresses come in link local, and they look like this. Unique local, global addresses, multicast, and special addresses. And here's what they all look like. We're going to talk about each one of them barely. Okay, again, we're not going to talk about this a lot, but I see happening in the next couple editions of our book, which I was hoping this one would, they would be putting more IPv6 and more they're not. All right. Let's talk about link local first. Internal networks. So now if we want to address just used inside this room, we can use a link local address. It says can communicate with hosts on the same network internally. Cannot be routed between networks. In other words, if we had router at the end of the hall, we could not go across the router. It's kind of like a broadcast address. Okay, cannot be routed over the internet. Every address has a link local address. So in other words, even if this machine here has an internet enabled address, it still has a link local address. Kind of like that loopback we looked at, that 127.0.0.1. That's an internal address. So we all have one of these. Okay, so all addresses have that. The first 10 bits are always 1111, 1110, 10. The next 56 bits are always 0. And CIDR, we haven't talked about this yet. CIDR stands for Classless Interdomain Routing. Basically, how we mentioned kind of the whole ABC network for IPv4? That's gone. Now we use something called CIDR. But, again, we're going to cover that more later. But in that notation, here's what it looks like. So how does this and that get translated? We'll see. Okay? Here's an example. We could have a %12, we could have a %13. Okay, the last 64 bits represent the host ID or the interface ID. So what the heck? How does all that work? So FE80, 1111 was F, 1110 was E, 1000 was 8, and 0000 is 0. That's how we got FE80. That's how we can convert the binary to hex. Okay? %12, it distinguishes among the multiple networks. You can put some numerical, I could say, I'm number 15. And now we can have multiple addresses in the same area, one's 15, one's 14. So, easy enough. So far, so good. You don't need to know this in depth, so you just get a general understanding of it. Okay? Now, unique local, okay? Used internal as well, but can be routed, but only between internal networks. So maybe we got a network in this room and a network across the hall. They're on two different networks. We can route across them. Can't surf the web with them. But maybe if I'm going to teach you how to do routing with a bunch of different Cisco routers, it'd be an awesome address to use. Because we could go across routers, we just can't get on the internet. Okay? Kind of like you got a learner's permit. All right, first 8 bits are always 1111, 1101. The next 40 are the global ID or site-specific address. Kind of like row state. Okay? The last 16, the subnet. And CIDR, we got FD00. Tell us how we got that? Obviously, the F comes from here. The D comes from here. And then 00, because you can always live off zeros. Last 64 bits represents the interface. And there's what it is. Okay? Global addresses now can be used on the internet. The first bits are always 001. And it says the network prefix always begins with 2 or 3. What the hell? Well, obviously it's on the next slide. I'll show you that in a second. The next 45 bits are the global routing prefix. The last 16 is subnet ID. So then, why do I have 2000? Well, we'll see that in a second. It says IPv6 routers only forward addresses starting with a 2 or a 3. Every other packet gets dropped, which is kind of nice. So someone can't, create some internal or some other numbered address and try to use it on the internet. It's not going to work. All right, so why 2000? So basically 0001 could either have a 0 or a 1 after it. That way we would get a 2 or a 3. Okay? So that's how we got that 2. Okay. Multicast address. Multicast is for multicast communications. Don't you like that? When you see the definition includes the word. What is multicast? Multicast is when you multicast something. So, yeah. Basically, multicast is when I want to image this room. I can send out packets with Ghost in multicast, which means you all answer it. It's kind of like its destination is everybody. But I send it out one time and everybody gets it, which is kind of nice. Rather than me having to send out 20 gigs there and 20 gigs there and 20 gigs there, I just send out 20 gigs one time and you all get it. So. All right, first 8 bits are always all 1, so obviously that's FF. Next, four are flags to determine the state of the address, temporary or permanent. And last, the group ID, and so on and so forth. Again, we drop all routers that are 2 or 3. Obviously, that's where the FF00 comes from. Okay. We also have special addresses. There's our loopback address. ::1 replaces that 127.0.0.1. Kind of handy, isn't it? Okay. We could have mapping addresses, 6 to 4 addresses. Okay, what do you think? Any idea what a 6 to 4 might mean? How about IPv6 to IPv4? Okay. Teredo, Multicast, also some reserved for documentation. So, there's a lot of addresses we're learning, addresses we can't use. So maybe instead of 50 octillion, you have 49 octillion. Still think that's plenty. All right, here's some examples. All right, this happens to be one of my machines. Actually, I'll show you on this machine. All right. Do I have the IPv6 disabled on these? Kidding me. Oh, there they are. See the addresses up there? Okay. And we talk about the link local. We talk, okay, link local, and we're going to see the other ones in a second. But, so here's some examples. Okay. Get back on my slide. Okay. Now let's talk about usage. IPv6 over IPv4. It says tunnels can be created. What's a tunnel? Anyone know what tunnel is? What's a tunnel in driving wise?
Go straight through something.
Okay, we can go through a mountain, we can go under a river, whatever. With this, we can actually tunnel IPv6 over IPv4. In other words, we're going to make a tunnel that connects the 2 IPv4 addresses and shove IPv6 through it. Easy enough. So we could do router to router. Obviously 2 routers talking to each other, or maybe my computer's talking to a router. I could create a tunnel between my computer and a router, or the router and my computer, or between 2 computers. So I could do this different ways. Okay. ISATAP. There it is right there, if you actually look. Okay. That's the type of address. Okay. Intra-site automatic tunneling addressing protocol. Who the hell's ever going to remember that? All right, so it says IPv6 transition mechanism meant to transmit IPv6 between dual stack nodes on top of IPv4. So in other words, we can start using IPv6 while we're still using IPv4. Because people aren't going to want to switch. I know a lot of people already have, by the way. Okay, it's a method of generating IPv6 from an IPv4. So here's our IPv4 address. We can actually use this. Or this. So how do we go from this to this?
You can hide the zeros.
All right, so these colons, basically we got 1, 2, 3, 4. So obviously how many groups of zeros are we missing? 4. 1, 2, 3, 4. Very good. Okay, then we got the IPv4 address at the end. What the hell happened there? Isn't this added? Remember, 5EFE, and we got that. Now, what the heck is that all about? Well, let's look.
Converted it over to
192 is C0 in hex. 0 is obviously 0. 2 is obviously 2. And 143 is ZF. So that whole IP address becomes that. C0, 00, which is the first 2, then 28F. So that works? It's kind of cool the way it all works, actually. You might not think so. All right, 6 to 4. Used when migrating from IPv4 to v6. You can tunnel over an IPv4 network. We talked about that. So it stores the IPv4 address, then encapsulates it. Then it says encapsulate the IPv6 packets inside the 4 for transmission. And we'll see a picture of the header. So now what we're doing is we're taking our IPv6 packet. We're sticking an old IPv4 address on it, sending it across. So to the whole world, they think it's an IPv4 packet. All right, Teredo, it's right there. Okay. Allows IPv6 hosts to communicate over IPv4 networks. Works only with NAT that support UDP. Y'all remember what UDP was? I think we mentioned it just a little. It's User Datagram Protocol. It's connectionless. We had TCP or UDP. TCP is a connection oriented, UDP is a connectionless. Okay? So it should always be implemented with a client-based stateful firewall. We're going to cover more about those later. So, now, what does that really mean? It means a platform-independent tunneling protocol developed by Microsoft provides IPv6 connectivity to nodes that are located behind an IPv6 unaware NAT device. There's a way to use it with the stuff that doesn't have a clue what you're doing. Okay? All right, here's the RFCs. It says we propose. What an RFC is, I don't know if I mentioned this to you guys before. RFC is a request for comment. Whenever you want to do something on the internet, you create what's called an RFC. You go to IETF.org and you say, I propose a new thing. It's going to be IPv12 or something. And they give you a number. They say, okay, you're now number whatever. This one happened to be 4380. And here's what they propose. A service enables nodes located behind one or per IPv4 address installations to obtain IPv4 connectivity by tunneling packets over UDP. Call this Teredo. Running the service request to help Teredo servers and so on and so forth. Okay? Basically, this is what they proposed and they made it. The reason it's called an RFC is the request for comment. Hey, here's what I want to do. What do y'all think? Then everybody comes back and says, boy, you're an idiot, or that's a good idea, or we make a few modifications to it, and sooner or later, we're all happy and we implement it. Okay? All right, let me stop there.